All right, good morning, everyone. Let's see. Hey, so today we're continuing with 4.2. Yesterday, we learned some of the tools that we're going to need for tomorrow. Summation formulas, segment notation. We're going to see that more tomorrow. Today, we're going to begin to kind of move towards the idea of area under a curve, which is we're going to want to talk a little briefly about how that is the inverse procedure of what we experienced in the first semester. So first semester was all about slope, all about derivatives, right? And derivatives derivative is just a fancy word for slope, right? And it's all about rate of change. And if you think about slope, slope is change in y over change in x, right? So much like how you learned math over over the years, we always learn something and we always learn how to undo that process, right? So we started with addition and then we learned subtraction, right? We learned multiplication and then we followed it by division, right? And all those processes just kind of undoing the process that we initially learned. So with derivatives, you see how slope is kind of division related, right? It's y2 minus y1 over x2 minus x1. This gives us the steepness or the rate of change of a specific point or between 2 points. So this semester, we're undoing the process of derivatives. So we're calling it antiderivatives. But let's look at how the order, let's look at the operations that we're using here, right? So this is mainly division, right? And how do we undo division?
Multiplication.
Multiplication, right? So let's think about in terms of multiplication, right? So if I want to undo this, it would be x2, or the inverse procedure would be x2 minus x1 times y2 minus y1. If you think of x2 minus x1, that is going to be some horizontal distance, right? y2 minus y1 is going to be some vertical distance. And if I multiply a horizontal distance by a vertical distance, the result that I get is an area of a rectangle. And that is why area is going to be very much related to the inverse procedure of derivatives called antiderivatives. So when we go through a process of antiderivatives, we're going to be able to achieve area related information. And we're going to use this process to help us find the exact area under the curve using calculus. But at the same time, it's also undoing the process that we learned with derivatives, with slope. But before we get to the calculus portion of finding exact area under the curve, we're going to first focus on the estimation portion of it. And the estimation portion of it is going to be helpful for us to see how that bridge is going to be achieved to get from approximation to exact area. Okay. And the easiest area formula that we have is rectangle. So we're going to start off, we're going to just be building, showing the different ways that we can estimate an area of a region using rectangles. And there are different ways that we can draw these rectangles. So that's what we're going to be doing today. But eventually tomorrow, we're going to see that bridge of connecting rectangles to moving from estimation to exact area. All right, so first, let's consider our graph. Let's consider a shaded region. We have x squared plus 1. That's a parabola shown here. We have our endpoints from -2 to 2. and we're looking at the region below the curve but above the x-axis. Suppose that we want to estimate the area of the shaded region using a given number of rectangles. So today we're not going to be focused on finding exact area. We just want to create these different methods of estimation. So we have four on this first page. We have four different ways of drawing rectangles. The first is using something called circumscribed rectangles or upper rectangles. And the way, if we are to go through this process of upper rectangles, we can ensure that these areas of rectangles that we create is going to produce a value that is an overestimation of the actual area that we see here. Okay, so right now we don't know what the exact area is, but we're going to create a situation that we know is going to be an overestimation of what we see here. So to ensure an overestimation, what we're going to do is for each subinterval, we're going to attach a corner of the rectangle to the graph. And this will ensure that the height of the rectangle is the same as the value of the function at the point where they connect. So let's say we have these four subintervals here, and I'm just going to give them x values here. Okay. So here's my first subinterval, second, third, and fourth rectangle. Now, if I want to create an upper rectangle, what I'm going to do is I'm going to look at my first subinterval and look at my two endpoints and see which endpoint reaches a higher point on the curve. So between f of -2 and f of -1, I see f of -2 hits a higher point on the curve. So I'm going to use that to represent the height of my first rectangle. Okay, for my second subinterval, I'm choosing between f of -1 and f of 0, see which has a higher point on the curve, and obviously f of -1 has a higher point than f of 0, so we'll let f of -1 represent the height of the second rectangle. Third rectangle, between f of 0 and f of 1, we'll let f of 1 be the height of the third rectangle. And then between f of 1 and f of 2, we'll choose the higher of the two, so f of 2 is the higher rectangle. So then if we do width times height for all these four rectangles added together, whatever the area, whatever that number is, we can guarantee it's going to be higher than the actual area over approximation. And we can ensure that because we can see that all these rectangles have segments that sit above the curve, which is going to guarantee a higher value than what we see here. Okay. Any questions with this concept? Now with lower or inscribed rectangles, this is where we're purposely choosing the lower of the 2 points on the curve and letting that be the height of each rectangle. So again, let's go from -2 to -1, 0, 1, and 2. First, second, third, and fourth. So between f of -2 and f of -1, I want to choose the lower of the two heights. So f of -1 is the lower height, so that's going to represent the height of my first rectangle. Between f of -1 and f of 0, I want to choose the lower one. Between f of 0 and f of 1, I want to choose the lower one. And between f of 1 and f of 2, I want to choose the lower one. So we can see that this rectangle is inscribed because we have gaps, but all the gaps are sitting below the curve and not above it. So we know that the areas of these four rectangles is going to produce a value that is guaranteed to be smaller than the actual area, produce an underestimation. Okay, we can also create rectangles where we're not so concerned about whether it's an over approximation or under approximation. We just want a consistent left endpoint to connect to the graph. we're always going to connect the upper left corner to the curve. So again, same graph, same interval. So for the first subinterval, instead of deciding between left and right, we're always going to choose left one. So here we'll do the first subinterval has a left endpoint. At the left interval is -2, so we'll do f of -2. Between -1 and 0, we know -1 is going to be the left of the second interval, and then we're going to choose left subinterval for the third rectangle, and then for the fourth rectangle, we'll also choose. Okay, so what's going to end up is you have portions that's above and maybe portions that's below, but we've achieved consistency of left-handed rectangles. And then right-handed rectangles is we're now going to be choosing the right endpoint of each subinterval to attach to the curve and letting that be the height of each respective rectangle. All right, so second page, we're going to practice finding upper sum and lower sum for these graphs. All right, so example 1. Use 4 rectangles to estimate the upper and lower sums for the area bounded by x equals 0, y equals 0, x equals 2, and y equals x squared plus 1. So here is the curve. Here are our boundaries. So the first step is we need to find the width of each rectangle. Right. The left and right endpoints are given to us. So we have right endpoint minus left endpoint divided by the number of rectangles. So my A value is 0. My B value is 2. And then my N value is 4. So if I take right endpoint minus left endpoint divided by number of rectangles, then I can get the width of each rectangle. Okay, so that's the first step. So I took this graph and I made it a little bit larger, so it'll be easier for us to work with. But we know we're going from 0 to 2 because those are our boundaries. And we have our A value, our B value, and our N value. And we're just going to plug into our width formula to find the width of each subinterval. So B minus A over N is 1/2. Take 1/2, and we're going to keep adding 1/2 until we reach our, so we can find the endpoints of each subinterval, and then we can make sure we can get to that 2. So 0 plus 1/2 is 1/2, plus 1/2 is 1, plus 1/2 is 3/2, plus 1/2 is 2. Okay, questions so far with these subintervals here? Okay, where did I get 4? 4 is at the very top here. It says use 4 rectangles, so we know that's our N value. All right, so now that we have our width, we're going to start off by finding the upper sum. So we're purposely going to create rectangles so that every portion sits nicely above the curve. So I'm going to use uppercase S to represent an upper sum, 4 to represent I'm using 4 rectangles. So here's where my first rectangle is going to be, my second rectangle, my third, and my fourth. Now, all of these, we're going to be doing rectangles, right? So just to remind us, our area of a rectangle is width times height. So we see that the width of each rectangle is going to be 1/2. We found that. So for my first rectangle, I know my width is going to be 1/2. My height, I'll be using the function to determine the height. But right now, I'm going to leave it in function notation. So I'm doing an upper sum first. So I'm going to choose the higher of the 2 points on the curve. Between f of 0 and f of 1/2, I see f of 1/2 is higher. So I'll let f of 1/2 be the height of my first rectangle. So whatever this value is, after I plug 1/2 into x and I get that value, 1/2 times that height is going to be the area of my first rectangle. Okay, and we're just going to go down the line with each of the other rectangles. So the second rectangle, also a width of 1/2. We have to choose between f of 1/2 and f of 1. Which one is higher? F of 1 is higher. So we'll let f of 1 be the height of the second rectangle. Okay, keep going. Width times height. Between f of 1 and f of 3/2. For the third subinterval, I'm going to choose f of 3/2. That's a higher point on the curve. And then between f of 3/2 and f of 2, I'll choose f of 2. And all these rectangles are safely above the curve, which will ensure that every rectangle will be an over approximation, which means that the sum is going to be guaranteed to be higher than what we see in this shaded region. Okay, we'll make the calculator do the work for us here. So if I plug 1/2 in for x, I get 1/4 plus 1, which is 1.25. 1.25 times 1/2 will give me 0.625. Okay, f of 1, 1 squared plus 1 is 2. 2 times 1/2 is just 1. F of 3/2, that's 1.5 squared plus 1. That will give me 3.25 times 1/2. That will give us 1.625. Again, we're just making the calculator do all the work for us here. F of 2, 2 in for x, we get 2 squared. 4 plus 1 is 5. 5 divided by 2 is 2.5. We add up the areas of these each individual rectangle, and we get 5.75. So we know that this is the upper sum. This number represents an over approximation or overestimation of the actual area. Under the curve. Okay, any questions here? All right, so now we're going to find the lower sum. Same interval, same width, same graph. But now The difference is now we're going to choose the lower of the two heights. So let me fill this in here. I have 1/2, I have 1, 3/2, and 2. So between f of 0 and f of 1/2, I want to choose the lower of the two y values. So f of 0 is obviously lower than f of 1/2. So my first rectangle will have a height of f of 0. Second rectangle, I'll choose 1/2, f of 1/2 to represent the height. And because the graph is always increasing, it's always going to be the left endpoint. Okay, but that's not always the case. But in this case, we're going to see that is what's going to happen. Okay, we spend the time to plug into our function to get that function notation to be a decimal value. And we're expecting a smaller value than the upper sum, right? Because we're creating these smaller rectangles. And sure enough, we do get a smaller value than the upper sum. Okay, any questions here? So one thing is that we know that neither of these are actual areas of our region. We know this is an overestimation, guaranteed overestimation. We know there's a guaranteed underestimation. So if I want to get a better approximation using these two values, I can find the average, right? So a better approximation out of these two, we can take the results of these two and find the average between upper and lower sum, and that'll just give us a better approximation. Okay, it's still an approximation. Doesn't mean that this is the exact area, but we do know that if we have a lower and higher guaranteed value, if we find the average, we know we're closer to our goal. Okay, next page. There's another way that we can create rectangles, and that is using midpoint rule. This is where, similar to upper and lower sum, in the sense that we're still going to be using the function to help us find the height, but instead of using the left or right endpoint, we're going to use the midpoint of each subinterval to calculate the rectangle's height. All right, so let's say we have the curve of 8 over x squared plus 1. We're going from 2 to 6, and they're telling us to use 4 subintervals. I'm going to redraw the graph so you can see how things progress. 8 over x squared plus 1 is going to be a curve that's going to look like this. And we're extending from 2 to 6. And those will end up being our a and b values. Four subintervals, so that's our n value. And then we can take that information and get our width. So 6 minus 2 over 4. 4 over 4 is 1, so that's our width. So to find the subinterval values, we're going to increment by the width and then mark them with the appropriate x value. So these are all going to be whole numbers. So you can see that we have 4 subintervals, right? So these are where we're going to be looking at for our 4 rectangles. But within each subinterval, we're not deciding between f of 2 and f of 3 for the first subinterval. Instead, we're going to find the average, the midpoint between these two endpoints. So 2 plus 3 is 5. 5 divided by 2 is 2.5. And we're going to take that midpoint and use that to determine the height of each respective rectangle. Okay, so between 3 and 4, 3 plus, we'll find the average of these two numbers. 3 plus 4 is 7. 7 divided by 2 is 3.5. $4.5 here. And 5.5 here. Okay, so here's my midpoint sum. Again, width times height. So the width is 1 for my first rectangle. The height is not f of 2, not f of 3, but it's going to be f of 2.5. Second rectangle, width is still 1, but we're going to do f of 3.5. So now we're just going to take these values and plug it into the function and get that decimal value, that height for each respective rectangle. So 2.5 in for x, 8 over 2.5 squared plus 1 will give us 1.103. Plug 3.5 in for x, 8 over 3.5 squared plus 1. $4.5 in for x, 8 over 4.5 squared plus 1. And finally, 5.5 in for x. Okay, we still have areas of 4 rectangles. But now this is going to be an even better approximation than either the upper sum or lower sum. And the reason why is because if you look at how these rectangles are drawn, you have portions that sit above and below the curve, so they're going to have a way of kind of balancing each other out, right? Unlike these previous rectangles where every overestimation is going to keep becoming less accurate, right? Every underestimation, right? Now we don't know whether this midpoint sum is an over approximation or under approximation overall, but we do know that this is more accurate than just the upper sum or just the lower sum. Okay, so again, it's a better approximation because each rectangle has portions above and below the graph. But just to make sure we understand, midpoint sum, this process is not the same as averaging between the upper and lower sum. Right? If we find the upper sum and lower sum and average the two of them, that's not the same thing as doing the midpoint sum. Okay, so it's a different process, not the same thing.
Should those numbers be close?
Maybe, but for our purposes, we're not going to do much of this. This is not going to be something. This is just kind of like a side note. And also, for our course, for this course, we're really not concerned about how accurate our estimations are. If we're ever having to do an estimation, we're just going to have to do the estimation that the problem tells us to do. So we're not in BC Calculus. We do a little bit of they do a little bit more of determining how accurate their estimations are with different process. But for us, we're just focused on we're not concerned about how the accuracy of our estimation. Now, having said that, we just have to understand that midpoint approximation in terms of rectangles is the most accurate. But tomorrow we're going to discover that there's another shape that will give us an even better approximation, and that's using trapezoids. So trapezoids followed by midpoint, and then the left or right upper sum and lower sum is going to be the least accurate. Okay, let's spend some time going over some homework problems that I'm just going to make it as part of our classwork here. So I have this link under today's notes. Either you can follow along, or if you had it printed out, you can do it on that sheet. Okay, so we're going to practice finding upper sum and lower sum with 31. So we're going to find the area of the shaded region. The shaded region didn't come out clearly on my copies here, but we're going to do upper and lower sum using rectangles, and each rectangle we're going to do a width of 1. Okay. I duplicated 31 so we can have different graphs to do upper sum and lower sum. Hey, let's do an upper sum first. So I have 4 subintervals here. Each has a width of 1. And I have to decide between each left or right endpoint which one hits the graph at a higher point. So we see between the f of 0 and f of 1, f of 1 is obviously higher. So we'll let that be the guide, be the representation for the height of the first rectangle. So we have 1 times f of 1. Now, the nice thing about this is that we don't have the function for f of x, but we do have a guide for the y value. So we're just going to look at our y-axis to determine the height, and we don't have to plug it into a function. So we see the height is at 3, so 1 times 3. No need for a function to find the height for this problem. Okay. For the second subinterval, we see between f of 1 and f of 2. F of 2 is higher up on the, hits a higher point on the curve. And f of 2 lands at 4. So that's a y value of 4. For the third subinterval, we're choosing between f of 2 and f of 3. F of 3 is higher. And then finally, between f of 3 and f of 4 is higher. So this height looks like it's around 4.5, so make our best guess there. And then f of 4 looks like it lands right at 5. Okay, we total those up, and we'll get 16.5. So this is guaranteed to be more than the actual area because every rectangle has these portions that stick above the curve, producing a higher than exact value. Okay, let's do a lower sum. If we do lower sum, we know that we're expecting estimation that's going to be smaller than 16.5, right? So still the same width, still the same graph, same subinterval. We're just choosing a different height now. So for the first subinterval between f of 0 and f of 1, we want to choose the lower of the two. So f of 0 is hitting a point lower on the graph. For the second subinterval, we want to choose f of 1 versus f of 2. F of 1 is lower. For the third subinterval, we want to choose f of 2. And then for the last interval, we'll choose f of 3. Okay. So width times height, width times height. We add those together, we get 12.5, and just like what we expected, we get a smaller number because we have an underestimation versus an overestimation. Okay, any questions so far? Hey, let's look at 33. Finding upper and lower sums for a region. So now we don't have a guide on the y-axis anymore. We're going to have to rely on the function to give us that y value. Okay, but first thing we're going to do is we're going to find the width. Width is b minus a over n. The rectangles are already drawn for us. We can tell that our left endpoint is 0, and we're ending at 1. So a is 0, b is 1, and we can count that they've created 4 subintervals for us. So we know our n is 4. Okay, so b minus a over n will give us the width. Which is 1/4. So we'll take that 1/4 and we're going to start at the left endpoint and keep adding 1/4 so we can determine the x value of each subinterval. So plus 1/4 is 1/4, plus 1/4 is 1/2, plus 1/4 is 3/4, plus 1/4 is 1. Okay, let's do an upper sum first. And we'll save this for a lower sum. Okay, width times height for each rectangle. Every rectangle has a width of 1/4. The height, we want to choose the higher point on the curve. Is it f of 0 or f of 1/4? F of 1/4 is the higher one. Okay. Next up, between f of 1/4 and f of 1/2, we want to choose the higher of the two subinterval. F of 1/2 hits higher than f of 1/4. Okay, third subinterval. So let me name this. So first subinterval, second, third, and fourth. So in the third subinterval, I'm choosing between f of 1/2 and f of 3/4. F of 3/4 is going to win out. And then between f of 3/4 and f of 1, we'll choose f of 1. Okay, and now we have to use the function to find the exact, or to get that decimal y value. So if I do 1/4, square root of 1/4 is 1/2, 1/2 times 1/4. And we just go down the line here. So square root of 1/2 to get my y value there. F of 3/4, so plug 3/4 into the square root. And finally, f of 1, square root of 1 is 1. Okay, use the calculator to total that up. We get 0.768. All right, let's finish up with lower sum for number 33. Same width, same subinterval. Width of 1/4, but now we want to choose the lower of the two heights. So between f of 0 and f of 1/4, I want to choose the lower height. So f of 0 is going to be the first one. Between f of 1/4 and f of 1/2, I'll choose f of 1/4. Between f of 1/2 and f of 3/4, I'll choose f of 1/2. And then finally, choose f of 3/4 over f of 1. Okay. Evaluate each height using square root of x, and then total the areas together, and we get, under approximation, we should get a smaller number than this, right? And we're going to get 0.518. All right, any questions? So these are coming from the homework problems that I assigned for today. So if you follow along, then you've already completed some of your homework here. All right, last thing I want to talk about is just something I talked about with the syllabus yesterday. Let me share that screen again. Okay, so tonight your homework is still from 4.2. You should be able to find the page number, the textbook problems, solution, and everything that you need on that chapter 4 page. So if you're not able to find something or see something, let me know. Now, I think yesterday I talked about how your homework could account for 5% of your grade, but I think they're still trying to figure out exactly what will be counted towards your semester grade, and they want consistency across all the math classes. So I think things are still up in the air, but it looks like right now, it looks like homework is not going to end up being part of your grade. It's just going to end up being quizzes and tests. And so it's just now a matter of figuring out what percentage test is versus quizzes, and also how many tests versus how many quizzes. So I think we're going to be able to get a much clearer picture once things are finalized, and that probably won't occur until next Wednesday. So yeah, I jumped the gun a little bit. But I talked yesterday about homework being 5%. Now, having said that, even though homework may not end up impacting your grade, it's still indirectly going to be helpful. Well, first off, because it'll just give you additional practice to prepare you for the quiz or test. And second, homework assignment, all these homework problems are going to be prerequisite if you want to do recovery on a test or a quiz. So I still encourage you guys to go through, keep up with the homework, because if you need to do recovery, it's already there for you, and you won't have to scramble last minute to get everything done. Okay. All right. Do you guys have any questions for me regarding that? All right, that's all I have. Hope you guys have a great day. I'll see you guys tomorrow, and we'll finish up 4.2 tomorrow. Take care, guys.
Thank you for seeing. Have a nice day.
You too. Have a good day.
Thank you.
Thank you.